Hello, everybody, and welcome back to Analytics Mindset. In this episode of Data Analytics Computing Follow Along, we will explore a very powerful machine learning model called random forest for both regression and classification, although we will focus on classification. As a reminder, I go through very high-level statistical concepts and programming concepts in this series, but my focus is on how to implement the models on Python preferentially. With that being said, I will go forward and move through this model. This was actually one of the most complex models I saw when I was looking at basic modeling, and the first predictive model that became an ensemble model for me. And that is one of the reasons why I made this video for anybody that wants to learn more about this and wants also some instructions on how to perform it step by step. Let's start by getting the packages. First, we're going to need to import pandas as pd, numpy as np. I just give them those aliases because I'm used to them. From sklearn, we're importing a lot of stuff. We already saw in some of the other videos classification report and confusion matrix. Matplotlib, we do not use it, but it's always good to have there. Here's the random forest classifier, and here's the random forest regression that I use for both classification and regression, respectively. We will also import tree because we are actually going to compare them to decision trees. And finally, from sklearn model selection, we will also import the train test split. This is very important as we have not used this before. It will make more sense why we're using it later on. Let's go ahead and import all of this. After all of that has been imported, and as a reminder, you can just press here if you're in Spider, or with that shortcut over there, CTRL return. Random forests are very powerful, as I already mentioned, with some caveats. For our purposes, we will think an ensemble model as a model made up of different models inside it. There is a way more advanced statistical definition that I will not go into today. If you're curious, I leave resources always in the description, including the data and the script if you want to play around with it yourself. If you do not have the packages, again, you will need to go through these commands here. You can just run them in the console, or you can run them directly from here. This dataset particularly is about traffic accidents in Arizona. We will be using PD read CSV to get it. This is my path to the file. I saved it in my local in a folder called videos. There's an accidents dataset, and then this one is called accident CSV. There's actually multiple files in this dataset, but I decided to go with the accident one. We will go ahead and import that as a pandas data frame. Here you can see it is a data frame. Now we can see the shape here in the variable explorer, but we will also just do it ourselves because why not? As you can see, we have 80 columns and almost 2,000 records. This is where having a subject matter expert is going to help a lot. We will take a subset of data that I already have decided beforehand. In the real world, you do not have that luxury. Mostly is I have this data or I have this insight and I want you to model something. That is why having a subject matter expert or somebody closer to what you're trying to do helps a lot. In this case, we are taking the data frame and then these square brackets are slicing it. We are using double square brackets because we have multiple variables and we are calling their names here. If you're curious how the names look like, we can actually do this. If we go here and we double click on accidents df, it actually loads it. Here you can see all the columns names here. And again, there are 8 of them. There is quite a bit of stuff to see about that. Some background about this data. VE is the total amount of vehicles involved in that accident. PDS is the total number of pedestrians. County name, self-explanatory, the county that is happening in Arizona, Manhole lead is the manner of collision. Feros is the number of people that died in the car accident, unfortunately. A interlead says that if the accident happened in an interstate or not. And finally, a DAO lead is the day of the week that this accident happened. We can see first if it has any null values. We need to be aware of that because scalar cannot take null values. And I actually forgot about that. There you go. There are no null values. If you have seen some of my other videos, you remember we had null values. In this case, we do not. Therefore, we don't need to drop them. For a classification problem, we will use the county name as a prediction. And it's going to be a little bit clear later on. For regression, we will use fatalities as a prediction. And that is pretty self-explanatory. If we have all this data, we want to predict if this accident looks like this, more or less how many people are going to die from this accident. It might not make a lot of sense in the real world because obviously we will mostly get this data after people have died, but is a regression problem that is pretty self-explanatory by itself. All of the features besides themselves will be used as predictors. When necessary, the regression problem actually has a caveat here. First, we will see the unique values for the categorical variables. We will go ahead. As you can see, these are the unique county names here, and this uses unique. You can go ahead and look at this one too. Let's look at I interlead. That should only have no interstate or unknown. And the day of the week, weekend, weekday, unknown. We will recode county name for this exercise. Why? Because we are going to use it as a yes or no question. We are going to recode everything that is not in Maricopa County as other counties. We will also filter out this value called 999, as you can see here, because it is here, and it does not make sense for a county to be called 999. Most likely it's just a placeholder for other county, but we are going to play it safe and just drop it. Here we are filtering by first taking the county name from the accidents DF sub. We are saying whenever this is not equal 999. If we run this, it's going to return us a lot of Boolean values. As a refresher, Boolean values can be true or false, but then we can use that and we can actually filter out the accidents DF sub. So we are basically using the data frame to subset itself and then assign that to another data frame. This is basically a very explicit filter. Okay, you can see our new accidents DF sub 2 has 6 records less than the original data. From there, we're going to go to the recording here. For here, there is a ton of different ways you could do this. I prefer to use np-where from NumPy. You could have done an if-else logic. You could have created a function. I just prefer to use where. Where basically says, take this condition, whenever accidents DF sub 2, the county name is not equal to Maricopa. If it's not equal to Maricopa, say other. If it is equal to that, actually return me the value Maricopa. And I'm going to assign that to the same data frame. And we can compare that actually. Let's make sure that this works. We are going to first get this. And we can just get the county name instead. Here you can see we have the first 2 are different counties that are not Maricopa, but 3 and 4 are Maricopa. We run all this data. After running all of it, we know that it has been assigned there. We can just do this and see it again. We can just make a very small sanity check. I always recommend you to do this whenever you're cleaning data or making transformations, as it's working as intended. The first two were the Pima County and the Yavapai County. They are recorded as order. 3 and 4 are Maricopa County. And as you can see here, they are also Maricopa here. Therefore, our recording is working as we expected. And again, this is not that complicated. It is more about what we want to do with this variable. We will also need to record all the categorical variables to dummies. Dummy variables can be pretty complex. A very high-level introduction is that some machine learning algorithms require it, and specifically sklearn requires them when you are predicting with them. For this, we're going to use pandas getDummies. This function takes the variables that you want to take. In this case, I'm taking all categorical variables here, and then it's going to give you the dummies for those ones. Let's see first the data that we are feeding the function with. This is the data that we're feeding the function with. As you can see, this is categorical. It is not a number. It is this value or this value or this value. A lead can be a weekend or can be a week, etc. Weekday. Once we execute this, we can see what came through. Very high level, as you can notice here, this new column, these are 14 columns. With the original data, we only had 3 columns. A lead weekend is going to be 1 whenever A lead is a weekend. And it's going to be 0 otherwise. And that applies to every single one of them. For example, record 1 says weekend here. A lead weekend is going to be 1. Record 4, if we go to index number 4, we can see that it's not a weekend, it's a weekday. Therefore, it's going to be with a 0 here. And you keep going with that with every single variable. What this is doing is just splitting those variables and putting 0 or 1 whenever that is equal to that. A more comprehensive treatment of dummy variables and one-hot encoding, as you may know it, it's out of scope of this video, but you need to do that if you are going to use categorical variables as predictors. Now, we have assigned this to this data set, but we also need to have the original data set. For this, we can use something very simple here, pd concat. What is concat doing? Concat is going to bring this data set here, that we're going to bring it here, the data frame. And I'm going to say, give me the shape of it. You can see there, it has 7 columns. Then I'm going to take this one here. And same thing, give me the shape. 14 columns. Through the axis 1, that basically means you're going to paste them through the index. This is the index here. So you're basically pasting them together by putting them side by side. I will demonstrate that by creating that data frame first, and then we can take this shape. It has 21 columns, and this may seem silly to you, but again, Python is also an advanced calculator. At the end of the day, we can do this. 5 columns plus 14 columns. How much is that? 21. We have exactly the number of columns that we gave by putting them side by side. And just for a final sanity check, we can replace shape with columns. We have all the columns that we had on the previous 2 data frames. With that being said, and already now that we have our final data set, we can go ahead and just get the header. Let's just see, there you go. 5 rows, 21 columns. For the first problem, we want to know if we can predict if an accident will be Maricopa, given all the other variables, and this will be predicted with them. First of all, we already recorded these variables here. As you can notice, we created the dummy variables for them. We need to drop them from our X. X is your X value, your independent variable, if you're talking about statistical terms, or your features or predictors um, in other terms. It is what we're using to predict. We want to drop those categorical variables because we already have them, just in a different way, through dummy variables. And we're also going to drop counting name. Why are we dropping counting name? Because we are predicting. We don't want it in the data that we are using to predict it. It will be like predicting counting name using counting name, and that brings a whole sorts of problems. We will take this, and similarly to our concat function, we're doing it with axis equals to 1. Therefore, we're doing it through the index. If you go through here, you can see more documentation. And let's double check that our x is fine. Yep, we have the 17 columns that are after subtracting those 4 columns there. Our I is way simpler. Y is our dependent variable, or what we're trying to predict. It is just the counting name for the data set. We will start by feeding a random forest and then a decision tree and other data. Why? That will be important later on. Just remember now that we are going to do both models. We will see if there is an improvement on anything between the two models. This is how the syntax for the random forest looks like. We use random forest classifier, and as a reminder, we're importing that from scalar and ensemble. The number of estimators is how many decision trees are going to go inside the random forest. Remember when I told you that an ensemble model is quite literally a lot of different models put together. This is a perfect example of that. You take 1,500 trees and then you use them to make a random forest. This is something important that we need to talk about. Random state ensures that we will always get the same results over and over again. I will not go into detail about why is that the case, because you need to go into random numbers and pseudo-random numbers and other concepts, but think about it as this ensures that we will always get the same results. This is very important in the random forest because the name says it. It is random. We will get different results every time we run it unless we specify any number on the random state. It could have been 1, could have been 100, could have been 1,000, as long as it's on. OOB score is out of the box score. It is basically an alternative to scoring through, as usual, scalar models. We will not go into detail because it goes very deep into the math and statistics behind this model, but we want to have it for this exercise. We will call this RF underscore EX. This is just an arbitrary name. It could have been anything else, or we could have even just combined these two different lines over here and make it one. And that is one of the advantages of Python. Python is very flexible, and you can actually just code at your own style. This is my style. I prefer to have breaks over here, so we have space for comments. I know what I'm doing because of my comments, and I also leave space between code that is not related to each other, so it's easier for me to read too. I'm going to declare that variable. Now that I have that one, and see how the type is ensemble.forest random forest classifier. I'm going to feed it. Feed means I'm feeding the X data and then with the Y response. That is going to train the model in this data. Now, this has been, the forest is now fed onto the data. It is now, we can say that it's trained. Now that it's trained and we can use it for prediction. First, we're going to get the score of it. In this case, we're only getting the this. It is about 70%. Now we can compare with a decision tree. we are going to use a classification decision tree for this with a max depth of 3. Why are we doing this? Just because I want you to see why we will use a random forest and why not. We do this, we feed the tree, we already have the model, we feed the tree. After we have fed the tree, we can just score 67%. Now, what if we just grow the tree? If you recall from the decision trees video, what we're doing here is just letting the tree grow. Instead of limiting it to 3 depths, we are just letting it go wild until it doesn't have anything else to grow. Compare these two. What do you notice here? If you want to pause the video and see it twice, you can do it. But these two scores are exactly the same. Why would we use a decision random forest if we have gotten the same accuracy than a decision tree? The answer might surprise you. In this case, it has some logic behind it for classification, and this depends on implementations and modeling, but the random forest takes all these trees over here that we just created, and it basically says vote if this is going to be from this class or this other class. For this data set, it makes sense because the trees average just came out with almost the same rules as the base decision tree. Now, we usually want to train a model first on some data in a process called training. We have been doing that to a certain extent so far. However, there is another part that we have not talked about. Imagine that you train your model on some data, but then that's not the data that you're interested in, because guess what? You already have the responses. You already know what happened. You already know if that accident was in Maricopa County or not. Instead, we want to use this to predict on another data. If you want to take a second to understand that, please do that, because this is a very important part of this video. We want to split the data. We first want to train it on whenever we have our observations. And then we want to use that model to predict on new data that the model has not seen. We are testing the data. You may know this as a train test split. We have not done this so far, but we will see why it's important. And this is also very useful to simulate that situation when we want to basically predict on data that we do not have the response. We do not have the Y in the real world. We are predicting because we have no idea if that accident is going to be Maricopa County or not. We only have the other variables. And that applies to all predictive modeling pretty much. Then for this, we are going to use the train test split from sklearn. The syntax for here, and I will need to explain some stuff here. If you have never seen this, don't worry. Basically, train test split is this function over here. It takes your X, takes your Y. Test size is how big your test sample is going to be. And the rest is going to be your training dataset. Therefore, test is going to be 30% of the old X and Y, and 70% is going to be on the training side. Random state just ensures that we're going to get the same results because this is random. Every time we split it, it's going to give us a different result. Now, how will this look like if we just put into the console? You can see here is returning you a list, actually. We have seen lists before, but that is inside is what matters. We have different data frames inside this list. We are creating different data frames here. How can we take advantage of that? We can just declare 4 variables at the same time. X train, X test, Y train, and Y test. Each of them is going to be assigned one of these data frames on the respective order. And this is something that is inside the documentation of the train test split function. Here you can see some of the documentation and how you can read more about it in the user guide of Sklearn. We're going to go ahead and execute this. Now see how we have X test now, Y test, Y train, and X train. Now, something we want to be aware is that the data has too many dimensions to have an appropriate visualization. You may recall from the decision trees video that we could actually see outliers there. We cannot do that here. We are just skipping through some data preparation and validation that we probably should have done in the real world, just because to keep this video as short as possible. But for these kind of situations where you have quite a bit of data, let's just take Y train, that is where you're training your data. This is quite a bit of data here, where you have multiple values and multiple columns and quite a bit of rows per column. There are some methods to deal with this dimension reduction, feature selection techniques such as PCA can help you. But for a deeper discussion, see the cross of dimensionality. If you want to go more in depth about why this is a problem, I would recommend you going through multivariate statistics and multivariate analysis. That is a more formal approach to this problem. Now, what is the main advantage of the random forest algorithm? It is a black box model. It is a very complex model that takes, again, decision trees and takes into account a lot of those trees to make a prediction. It is based on the famous saying, the wisdom of the crowds. If you have enough people and you take their opinion on it, even if they are not from a certain background, you will have something useful from a very diverse crowd instead of relying on one single opinion. This is the basis of the random forest model. It is called random because each tree of the forest considers a random subset of features. Recall how in our decision trees video, each of those trees consider the features that we gave them. In this case, each of these trees is going to consider a random subset of features, and it's going to go through the whole 1500 of them. And then there is a lot more theory behind it. There is way more advanced ways to perform this as well and to use decision trees. Boosting and bagging are additional methods that we can use for that. However, I will refer you to an introduction to statistical learning that I always leave in the description if you want a deeper treatment on it. It is a very complex topic that you will need to go through most of the chapter on decision trees and random forests to get a decent understanding of, if you do not have it already. Now, let's import the random tree classifier again, the random forest. We are going to call this RF class. This is just another model because we just want to get a different model, and I don't want to override this one just in case we need it in the future. I'm going to use the same number of trees and the same random state. After that, we're going to feed it again, but notice the difference here. I am not using X and Y as always. I am using X train and Y train. I am training the model on the training data. That is why it's called train. The model is learning from this training data. But after that, I'm going to make my predictions. I make the predictions on X test. This is data that the model has not seen. With that, there is one visualization that I still want to get out of this. We cannot see each tree because there is 1500 of them. You can access the trees, that is again outside of the scope of this video. You can even plot them, but for the purpose of this video, we are just going to get the future importances. And this looks ugly. I don't know about you, but I don't like interpreting these things. Therefore, I can just make this a PD series for this visualization. I'm going to take the future importance, that is just part of the model here. As you can see here, it is the same part of it. And then the index is going to be X columns, the columns of my X. And we already saw the X there. That is what we're using. Finally, I'm also going to sort the values because I like sorting the values. And then we can plot it. For the plot, we're just using this plot here, and the kind is a bar. I want my bar plot. There is a lot of ways to create plots, but this one is probably the fastest way to create a bar plot from here. Here you can see the variable importance. PDS, the total number of vehicles, and how many people died seem to be by far the most important features for this model. There is 17 predictors, as you can see here. We will not see if the model can hold new observations. This is a contrast again with our decision trees video, where we actually confirm that the model we just create a rule that is going to put things that are more than their bounds and just keep increasing all the way to infinity. We will not demonstrate that again here. If you're curious about it and you have not seen it, please go back to the decision trees video. With all the predictive models we have seen, we can also, instead of getting the observation, because we can just get this and see the predictions. Say if it predicts if it's Maricopa or other, we can also just get the probability. This probability is how likely it is for an observation to be from the positive class, in this case, being in Maricopa County. Now, the second part of this is what we're interested in, is the probability of the accident being in Maricopa County, while the first one is just the probability that it's not going to be there. We're going to get that. And there you go. We get an array that is showing to us what is the probability according to the model. Now, let's get the score of this. The score, we're going to get it with the X test and Y test. Is 68%. We could have done it with the trained data sets, but that is not recommended. The best practice is on the testing side. Why? Recall, we trained the model on some data. Then we are basically trying to get the prediction from data that the model has not seen. This is comparing that to data that the model has not seen yet. And considering that the model has not seen any of this data, this is a pretty decent fit actually. Now we're going to compare it with the classification tree. You have seen me already executing line by line. Now something you need to know is that in Python, we can just execute chunks of code like this. I'm not going to execute each of them. I'm instead going to execute the three of them. Let's see what happens. I got the score. Why? Because first, Python went through this to import the decision tree classifier. Then it fed it with the train data. And then it gave me the score for the testing data. All of that in a single execution. If I were to have put print on each of these ones, I would have gotten 3 outputs, but because I only did the last one, I'm only going to get the last output. This is pretty useful if you're executing stuff from the console, or you just want to go deeper into how Python works, or you're executing from the command line, for example, too. That is also an option if you don't want to use an IDE. Now, if we compare this increase with the original one, is around 3.5%. That seems rather low. Let's compare it with the whole tree. We're just going to let this tree grow. Instead of saying that the max depth is 3, we let it grow and see. There is barely any difference between these two models here, at least in the scoring. We can also get the confusion matrix here. You can see there were 135 observations that are true positives. They were positive in the data, and they were also classified as positive by the model. And there are 244 true negatives that were classified as negatives and are also negatives. We can also get a classification report, and you can explore more in detail if you want. Now, what if we do the same without the recoding, without everything being from Maricopa account? This is expanding our classification to multiclass or multinomial classification, where we are trying to predict multiple classes instead of just 0 or 1, yes or no. Is this in Maricopa County or not? We're going to get again this data frame. And now we're going to create categorical variables. Same thing as before. The only difference is that we are not recoding in this case. You may recall this code. It is exactly the same. The only difference is that from here now on, I am using different variable names in case I need to go back and just see the old model. So these data frames do not override my old ones. I'm going to call this XM because, again, I do not want to override it. In this case, I'm dropping again the categorical variables because they have been already, they are already in the data as dummy variables with drop. And then I'm going to get my Y, that is country name. I could have done the old Y too because it is the same, but I just prefer to use this one. Now we're going to do the same thing as before, the train test split, but notice how I'm using X underscore M, Y underscore M, and I am also creating 4 new variables that end with M. If I do this, we can verify that X train has not been overridden. If we add an M here, we can see they have exactly the same shape. Are they the same though? They are not the same, as you can see here. And that will be important. We have created another variable without replacing the old one. In case we need it into the future, this will be important. Now we can feed our random forest too. Let's create this one. This is just a new random forest and has 1500 trees. We're going to feed that on our new M data. There you go. And now we're going to score it. 38%, that is worse than before, in part because you have so many different counties now instead of only one to predict. We can check on y_score m. You can see here we have the whole data in contrast with the other from the original one. Now we have this whole out-of-bag score. I'm not going to go into a lot of detail about it, but it is an alternative metric to see the accuracy of the tree, of the forest, based on the forest itself, without the train test. As you can see, it is very close to the actual score that we calculated through the score method. We will compare it to the classification tree. I'm just going to go ahead, do this. Now, our classification tree was actually better than the random forest. Let's just see the full-grown tree to see if that's better. That was also better. What is happening here? Why is the random forest worse than the both trees? This is something that I do want to discuss. The random forest model is way more complex than a simple decision tree. However, not all is not going to be better always. This is something that I really want you to understand. There are way more complex models over there. Neural networks, for example, can get very, very complex, but they are not necessarily going to outperform simpler models always. Support vector machines are another example. Sometimes, yes, the simpler, the better. It depends on the data, but a simpler model cannot perform a more complex one. In that case, if the simpler model is simple or even just a little bit worse, it might be worth to just keep a simpler model. If I am doing regression on 50 variables, and then a regression in only one of them is better, then I will just use one instead of using 50. We could have done model tuning on the random forest to perform the decision tree, and other techniques too, but that's out of the scope of this video. We're only focusing on the baseline of the random forest. However, there are techniques. We decided to just have 1,500 trees. That was a random pick. We could have done anything, any number of trees that we wanted to, and there are techniques to do that I will discuss at the end of the video. But this is why we cannot just plug in a neural network to every single problem we want to. A simple model may just be better in a lot of cases, and that simple model is faster to compute. As you have probably seen, the random forest algorithm takes way more time to process than simple decision trees. We can access a lot of information from the random forest, like the estimators. Each of these is a decision tree, so there are 1,500 of them that we could access. And all of them are different than the other, or it should be in theory, different enough from each other. We can see what estimator was used. We know which one, the decision tree classifier. The decision tree classifier was used multiple times to create each of the simple trees that we see here. We can compare the class attributes. For the first model, the classes are Maricopa, that's Maricopa County, and other counties. For the RF2 model, though, here we have all the counties in this array. These are ordinal counties there that the model is trying to predict. We can also just get the number of features. How many features are there? There are 17. That is our 21 features, but less 3 of them that we got rid of. What are the outputs? The number of outputs, only 1. For the second one, it's also only 1. We only get 1 output, and that is our y, the prediction. With that being said, we will wrap up with random forests for regression. You may have noticed that I spent a lot of time on classification, and that is because there is way more stuff to talk about in classification for the random forest algorithm and based. Regression, see, it's usually more straightforward in these scenarios. We will recall the county name just because we are using it as a predictor in this case, and we are not predicting it. Same as before, we are taking NP where, and then taking the county name equals to Maricopa County. In this case, though, we are not saying other Maricopa. We are saying 0 or 1. How is that going to be different? Okay, you can see the new data frame, and if we just take the county name, 0s and 1s. So instead of having other here, we have 0s. Instead of having Maricopa here, we have 1s. This is just so sklearn can use it, because sklearn can support the classes as outputs, but not as inputs in the prediction. It cannot use them as predictors. We are going to generate a new X. This is called XReg instead for regression. You can see here, I am dropping almost everything there, and that's on purpose. XReg has 5 variables instead of the 17 that we had with our regular X. Y is only going to be fatals, so we are going to be predicting how many people will die based on this data that we have for new cases. And we are going to simulate having to use 70% of our data for testing purposes. How you can think about this is we do not have the data for these 70% of the cases, only for 30% of them. Does it make a lot of sense? Probably not, besides some extreme situations. But in this case, it does make sense to just walk through it. We're going to execute this to get our X train reg, X train test reg, Y train reg, and Y test reg. They have been created here, as we can see from the variable explorer. Now we're going to create a new random forest, but this one is different. We are using random forest regressor instead of classifier. Same number of trees, same random state, and with the auto-back score. We can feed the data there, and we are using the training data. We are feeding the model with the training data. And then we're scoring it onto the testing data. As a reminder, this is not the accuracy of the model. In this case, we're just getting the error of the regression. And we can also get the auto-back score because we have it here. As you can see, both of them are pretty close together. These are pretty small also. We are having a good prediction on how many people will die based on the features that we gave them all. Let's compare it with the decision tree regressor. As before, we're first going to have one which is max that is 3. And then we're going to just grow a full tree. Now, both of them are higher than the score that the random forest got, even though the full tree was pretty close to it, as you can see here. This is another way to demonstrate that sometimes just a simpler model is better. If you do not care about the loss in accuracy, you may just go to a full-grown decision tree, or even this front tree, because guess what? We can actually plot this tree. This tree with only 3 levels, we can actually plot it, we can explore it, we can see what rules it generated, etc. Things that we cannot do with the random forest just because of how complex the model is behind it, unfortunately. Let's get the feature importances. And we can, as before, just make a fancy plot. And let's compare the plots. The number of vehicles has a big weight on this predictive model for regression, for how many people died. The number of pedestrians comes second for obvious reasons. If there are more pedestrians, there is a higher chance that some of them will die because they are not protected by the car either, and they are most likely going to be hit. Weekday and weekend are also related, and unknown to a way lesser degree. If we compare these two models, we can see how they are different, and that is to be expected. We could say that for the classifier, the most important predictor is the number of pedestrians to see if an accident will be in Maricopa County or not. While for the regression model, it is the total number of vehicles that is going to mostly determine how the model is going to put how many people died there. Now, what is the main advantage of the random forest? The trees in the random forest are uncorrelated, or at least are supposed to be uncorrelated. This means that we are creating a ton of trees that should have at least different features. And in the case of regression, we are going to take some kind of averaging between them to get our regression output. The random forest does not overfit the data as much as decision trees, and that's why we actually get higher scores on average than the decision trees, because you have so many different trees voting in the case of classification or being averaged in the case of regression that it captures the relationship between the predictors and the prediction without overfitting. As a quick explanation, overfitting means that you're also fitting the noise of the data frame of the data set, specific instances that may not repeat later on. How we determine the number of trees again? We talked about this before. This is an arbitrary number that we use because it is nice and big. However, there are techniques that you can actually use to do something better than I did. If you want to try it by yourself, you could try cross-validation and hyperparameter tuning. Both of them could also improve the model. You could also perform feature selection before putting everything onto the random forest. There are some advantages or disadvantages to those processes. In this video, I was most interested in giving you an overview of both the random forest classifier and the random forest regressor. With that, I wrap up this video. I really hope you find it useful. Again, as a graduate student in data analytics engineering, I appreciate your like, your comment, if you subscribe, or any other feedback that you may want to give. Take care. Thank you. Have a good day.